Good morning, all of you. Let us meet with some important topics today. One is the geomagnetism, and the other one is magnetic materials. Both are very simple and popular topics for our examination. To begin with, geomagnetism. You know that Earth is a magnet. Earth produces magnetic field of its own, and the origin of this magnetism we never discussed in our session. We do with the characteristics of geomagnetism. Whenever we say magnet, magnet should be a dipole. Similarly, Earth, when acts as a magnet, it should be a dipole, such that, now look at this figure. Earth as a globe, when we consider, first let us say this is geographic north and this is geographic south. The north pole of the magnet and south pole of the magnet with respect to its geography. Now we say, when it is acting as a magnet, now again it has its magnetic north pole and magnetic south pole. Now it is quite interesting that here nearer the geographic north, magnetic south is present for Earth, and similarly nearer the geographic south, the magnetic north pole of the Earth exists. Therefore, now this is the magnet that we are talking about, which you can see it as in the form of a blue line. I have represented this one as a black line. So first thing that you observe is that when it comes to the Earth's magnetism, at geographic north, south pole is present, and at geographic south, magnetic north is present, and also you will find that these poles, the geographic pole and magnetic pole, does not coincide. So two things are there, poles being not coincide. Therefore, now we are drawing two vertical planes. One, this MGSG, what we call as geographic meridian of Earth, and another one is NM. This is what is the magnetic meridian of the Earth. So these are the two meridians that we have shown in the vertical plane. To tell you the same, this is how you will imagine. See, this one, supposing this one is what is the geographic meridian. Now I will just take one more plane, and this now becomes the magnetic meridian of the Earth. So this is what I have shown there. Supposing if this is what is meridian, geographic meridian, this becomes magnetic meridian, and they are always at some angle. So at a given place, the angle between the magnetic meridian of the Earth with geographic meridian is what is popularly called the declination. So since we have now drawn this angle, and do remember, this becomes magnetic equator for Earth. We have geographic equator. Similarly, we have here, this becomes the magnetic equator, such that this part is what is called as southern hemisphere with respect to Earth's magnetism. Whereas this part, this lower part, I will call it as northern hemisphere. Remember, in the northern hemisphere of the Earth, magnetic southern hemisphere is there, or vice versa. That is to be taken care here. And one more thing regarding declination. So two more points let us try to remember, that this angle of declination increases from this equator to poles. Supposing at higher latitudes we take, or at lower latitudes we take, the theta value will be different, such that the declination increases at higher latitudes. Second thing is that you will find when we are expressing this declination, how it is represented with respect to the magnetic meridian. You will see in the northern hemisphere, it is the angle towards west, because they have taken this geographic north. This is towards west, and in the southern hemisphere, this declination angle is towards east. So expression of this declination will be something like, supposing if it is in the northern hemisphere geographically, or else southern hemisphere with respect to Earth's magnetism. So this condition is important. This term will, complete term will have its significance in finding. Supposing if it says that 27 degrees is the declination at some point, then it means that this is 27 degrees towards west. Similarly, in the northern magnetic hemisphere, it will be towards east. These angles will be given as, so 27 degrees, here I call it west, whereas here some number, if I get the same number, I will write it as 27 degrees east. So this is one important part. And one more important point is, this declination, of course, is a constant value though, but over a very long period of centuries and centuries, this angle of declination will be changing. Earth's magnetic meridian keeps changing with the time, but the time is not years or centuries, even more than that duration, this will be changing. Now, one more important point regarding declination is that we use sometimes what are called as magnetic maps. So, with respect to magnetic maps, two important definitions, maybe for NEET and CET. When it comes to declination, I said the locus of points, locus of places joining same declination. Remember, same declination, and the declination not equal to 0 degrees. The declination not equal to 0 degrees, they are called isogonal lines. Isogonal lines, places joining same declination, whereas supposing, one more time I call it as agonical line. What is agonical line? Agonical lines are also the line or the locus joining the places of same declination, but this time that declination is 0. So at all those places which we call agonical lines, declination is same and theta equal to 0 degrees. So in Earth's magnetism, these are few things regarding declination. Now, one more time. Earlier we said we have this magnetic meridian of the Earth and geographic meridian of the Earth. Now here I have shown this vertical plane showing the magnetic meridian of the Earth. Supposing at a given place, in this magnetic meridian, B is the magnetic induction produced by Earth. It is the total magnetic induction. And we know our popular case of resolving into vectors. One component I am taking as BH, the horizontal component. So this is horizontal component of Earth, and this BB, this is what is the vertical component of total Earth's magnetic induction. Now we will find that this angle I am taking as some delta, an angle made by B bar of Earth's induction with BH bar, then this delta is what is called as dip angle, also called as inclination, Vector resolution, therefore our principle is that BH equal to B times cos theta, or I will write delta cos delta, if delta is this dip angle or inclination, and the vertical component will be B sin delta. Such that the same rule, B is under root, yes, B H square plus B V square, or else also tan delta is equal to BV by BH. All those results you will find squaring and adding or taking the ratio this one. And one more thing, in which of the cases we have to use BH and in which of the cases we have to use BV. You remember in electromagnetic induction, in the case of motion EMF, there I have specifically mentioned where we are using BV. One more time, if you have any doubts, go back and watch the session one more time. Now, when does we use BH, which is most popular? Most of the examples what we do is that in most of the cases we always take the case of a horizontal plane. So in the horizontal plane experiments are performed, therefore we in all such cases we consider this BH value. BH is considered most of the times except in the case of those who have strength in the case of motion EMF. Otherwise, experiments, horizontal plane, if it is Earth's magnetic induction, we'll always take it as BH. Now, again with respect to this dip or inclination, 2 or 3 important definitions with respect to magnetic maps. Earlier we said same declination, of course not being 0, isogonical. Same declination 0, that is what is called as agonical. Similarly here, delta same dip. If we take the locus, such locus is what is called as isoclinical. Remember, isoclinical, dip same, whereas delta is equal to 0, same dip but this time delta equal to 0, we call it aclinical lines. Aclinical lines. So this is also one of the important definitions you can remember. And one more definition with respect to the magnetic map would be, suppose BH is equal to same. Now we are locating those places on the planet where BH value is same, then that locus is what is referred as isodynamical lines. All these magnetic maps, you know, in biology you might have come across. Birds make use of these magnetic maps in the disk migration from one continent to another continent also. Such a huge migration of thousands of kilometers is possible through this kind of magnetic maps. It is said in your biology. So these are few important terms to be remembered regarding geomagnetism: angle of declination, angle of inclination, the dip angles, the relation, and of course about the magnetic maps. Now let us continue with the most popular case of neutral points in Earth's magnetic induction. Now, neutral points in the case of Earth's magnetic induction. Neutral point where the net magnetic induction is 0. For net magnetic induction to be 0, at least we need 2 magnetic fields such that they are equal in magnitude and opposite in direction. Here, we are taking the case of one naturally occurring magnetism, which is Earth's magnetic induction, and the second one is magnetic induction produced by a bar magnet. So the 2 cases we consider here are B and BE, and that too we are now taking all the cases with respect to a horizontal plane. Therefore that BE we take only the horizontal component BH. So remember, when we are taking the case of these neutral null points in Earth's magnetic induction, it is in the case of horizontal plane. Therefore B due to bar magnet. The 2 I am taking it as a short bar magnet, and the next one is BH due to the Earth, the horizontal component. Now, 2 different cases we are now discussing. First one, this is a horizontal plane, and this is a long bar magnet which is placed vertically. Magnet, remember, horizontal plane, and this is a long magnet placed vertically. Now, what is this meaning of long bar magnet? Earlier we said magnetic poles cannot be isolated, always exists as dipole. Therefore, now when it is a very long magnet, at any point on this horizontal plane, the effect is only due to one of the poles which is lying on this plane, and the effect of the other magnetic pole can be neglected. And that is why we are now taking the case of long magnet placed vertically. Then it does not represent the case of dipole, rather it represents only a monopole. That is what is the case now we are discussing. So this is a vertical plane, so we have to consider horizontal component, therefore BH, and another capital B is the magnetic induction produced by monopole. So now the condition is very simple. What is that? The B due to monopole is equal to BH due to Earth. Now what is this B, monopole, which is the same case as that of intensity due to point charge. You remember that case? Yes, mu naught by 4 pi small m, the pole strength, by r square, the distance at which we are now locating a magnetic null point from the magnet equal to BH. Equal to BH. This will be the mathematical condition. Look at this condition. M, the pole strength, small r, distance of null point. Supposing I got null point, and that location of null point is very important. We'll explain that. Supposing you got a null point over here, and this is what is the distance we are taking from the magnet, that is from the pole, not from the center of the magnet, from the pole. This is pole strength, this is the distance of null point, and this is what is BH. 3 parameters are there. Any two given and asking for the third. Now the question is that it will be a difficult one when it is asked with respect to the location also. And for that, now here I show this direction sense where we are getting that null point. Do remember, according to our earlier discussion, it is always magnetic north pole, magnetic south pole. Where do they exist? We have told. Because of the reason, BH of Earth's magnetic induction is always directed from geographical south to north. In fact, this we have already used many times in our previous sessions as well. Repeating, BH is directed from geographical south to north. Therefore, now you will see here in this case, this is what is geographic north. I am taking BH, 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 BH. Now supposing I have placed a magnet like this, and supposing here I have shown north pole lying on the horizontal plane. North pole, magnetic induction away from the pole, south pole, the magnetic induction towards south pole. Even in the case of dipole, axial point, we have shown the same case. Therefore, now here when you represent, what happens? Supposing north pole away, away, then B and BH will be perpendicular in east and west directions. Whereas, supposing here it is north, away from north, away from north. This condition will give you, yes, can you see this? This is a horizontal plane I am showing. A point due north of this magnet, place the magnet vertical. B and BH are parallel, and here south you have B and BH anti-parallel. For the existence of null point, the condition is anti-parallel. Therefore, now here the point is the two possibilities that it is due north of magnet. This north we are referring to geographic. Due north of magnet if yes, south pole, if south pole lies on the plane, and it will be located due south of magnet if north pole of the long magnet lies on the horizontal plane. So the location is to be taken care of with respect to careful observation which of the pole is now lying on the horizontal plane. Mathematical condition, and for the location which of the poles of the magnet is now lying is the important case. Now, this is the case of long magnet we have taken and placed it on a horizontal plane location. And how many null points we are getting? Remember, only one null point we are obtaining, which is lying on the horizontal plane. Right. Now the second case is, let bar magnet be placed in a horizontal plane. Earlier it is placed vertically on a horizontal plane. Now the plane of observation is plane, and our bar magnet is also placed in the horizontal plane, such that this time let us take for simplicity a short bar magnet. Now there again we have two possibilities. How is that? Now this is not a place vertically. Remember, board is a vertical plane. Don't just misunderstand. We need to consider everything in the horizontal planes. Supposing this is geographical, north, south, and therefore east and west locations are quite important. Now this is a magnet placed horizontally, such that the magnet is first placed along magnetic meridian of Earth. The first condition, magnet cannot be placed in any orientation and can obtain null points. No, it is not possible. The first condition is that magnet to be placed along the magnetic meridian of Earth, such that now here you see the magnetic north pole of our short magnet is facing geographic north, or else south pole of the magnet facing geographic south. So that is how we have placed it. Now let us discuss this in 2 to 3 details, so that not only the question of null points, neutral points, but also other examples also possible. And that is why now you take at any axial point I am talking. At an axial point, what is the situation, and at any equatorial point, what will be the situation. Now you see, this is geographic south north is taken, so at any point BH is always from, yes, south to north, south to north, south to north, the same vector BH at any point. Whereas now let us write B due to the bow magnet. B due to bow magnet, short magnet I am taking. Therefore, if it is the case of axial point, look at this axial point. It is nearer to south, therefore it is towards south along the axial line from south pole to north pole. In this case, here again you will find this B. Therefore, your figure shows that at an axial point, yes, B due to magnet parallel to B due to H. This is the first condition. Therefore, net magnetic induction is always B plus BH. And what is the direction? Yes, it is always geographical south to north, you are getting B plus BH, because BH is also, according to us, south to north, BH is also south to north. Therefore, it is south-north orientation, the net magnetic moment we will get. Whereas, now, at an equatorial point, you see, equatorial point, yes, at an equatorial point, draw the B vector again due to dipole, parallel to axial from north pole to south pole condition, yes, north pole to south pole, here also north pole to south pole. Likewise, we consider any point on the equatorial point, what we find is that B bar opposite to B H bar. Here it was B bar parallel to B H bar, and it is opposite. Therefore, the net induction is B difference BH I am writing, higher minus lower value we consider. Therefore, now at any axial point it is always B plus BH, and the direction is from geographical south to north, but at equatorial point now we get 2 or 3 cases. What is that? Now, supposing we said B bar and BH bar anti-parallel, therefore it is B minus BH, and in the case if B due to magnet is equal to BH, supposing I have shown these 2 points here, and they are equidistant points here I have taken. One I call it as N1 and another I call it as N2, such that at these 2 points N1 and N2, B and BH are anti-parallel and also equal in magnitude. B is equal to BH in magnitude. B bar is equal to minus BH bar, vector notation, right? B bar is equal to, so I am now writing for it, scalar only. B is equal to BH and of course anti-parallel. Then these N1 and N2 will be 2 null points we are getting. Remember, where do we get in the 2 null points? North pole of the magnet facing geographic north or south pole of the magnet facing geographic south. We are getting 2 null points, one due east and then the other due west. Such that, ideally speaking, this distance from the center vector can this as R, and also here also we get at the same distance R. Now R is not a distance between null points, but it is the distance of a null point from the center of the magnet. So here R refers to distance of null point, therefore B is how many null points? 2 null points. Direction, one due east and another due. Therefore here now I am writing the condition mu naught by 4 pi for a short bow magnet, m moment of the magnet by R cube, distance of null point equal to BH. Earlier you got one expression where you got mu naught by 4 pi, small m by R square, it was due to monopole, remember. Here it is m by R cube, the dipole factor. Therefore one more time, moment term, distance term and BH term, 3 terms are given and anything can be asked like that. Therefore now you see what is that we can make different questions are possible. Within this null point, at any point, what happens? Here at null points, B is equal to BH. Within this null point, B greater than BH. Yes? Because lesser distance, more value of B, B proportional to 1 by R cube. Therefore, within this null point on either side, the resultant induction will be from south to, it will be from north to south, geographical north to south. Exactly at null point, net induction is 0. Beyond this point, beyond null point, which dominates? BH dominates. B will be less than BH. Got it? Within B, within the null point, B greater than BH, net induction is from north to south direction. Whereas beyond null point, it will be, yes, B minus BH, BH greater than B, then it will be towards north, that is south-north orientation we will find for the net magnetic induction, like that. Now number of examples we can go on doing like anything. What is that? See, one example I would like to show you. If you are ready with this condition, you see m by r cube not to 2m by r cube because of the equatorial point conditions. Look at the points for axial point and equatorial points. Now, let me just do one example which happens to be very, very tough because we have to make use of two simple conditions. Two simple conditions. I said north pole of the magnet, north pole of magnet facing geographic north, geographic north, yes, null point is at a distance d. Simply nothing is said. Simply, no directions. Simply they said that null point is at a distance d. If BH is equal to some number I will take. Suppose it is given as some 30 into 10 power minus 4 Tesla at some given place. BH value is 30 into 10 power minus 4 Tesla. Find net magnetic induction. Find net magnetic induction. Different possibilities I am writing here. At an axial point at a distance d. Second one, at an equatorial point. Equatorial point. Instead of saying axial point also, see, at a point east of, sorry, I will say, yeah, north of magnet at a distance d. Another one, at a point east of magnet at a distance. This time I would like to change that as a 2D. See how difficult example now it appears to be, though it is very simple, because we need two conditions, B versus R, distance induction relation for a bar magnet, coupled with the idea of B and BH in the case of neutral points that we have now discussed. Now according to this north pole facing geographic north means null point is at a distance D, means that D is yes, towards east or west, right? Towards east or west. Therefore, now north of the point means, so for question number 1, what is the answer? What is the answer or solution? Now at a point due north, B net, we know that it is B plus BH. Earlier our discussion should tell you at any axial point B and BH being parallel. So it is B plus BH. Now the point is that at a distance D, B is equal to BH, equatorial point. Null point means B due to magnet is equal to BH of Earth. So now, same distance if we consider axial point, same distance, equatorial becoming axial, the induction will be double, you remember, same distance point. Therefore, now B due to magnet is 2BH plus BH. Why you got this 2BH, you tell me? Because D distance null point means east or west at a distance D which are on the equatorial point, B is equal to BH. Therefore, same distance axial point I consider it will be double the induction. Clever questions these are called. Clever questions. Therefore, it is 2BH plus BH and answer is 3BH. 3 unit. Supposing in the next example, see B what happened. Now we are writing, it was earlier case of axial point we have taken. Because those directions, he is not mentioned whether it is axial point or equatorial point, but the sense of direction should tell us whether it is axial point or equatorial. Because for the part B of the example, he said it is east of the magnet. So east west, where we get equatorial point when north pole facing north. Therefore now here B net is equal to, remember, the distance is given to be 2D. That is a point which is beyond null point. Earlier we said within null point and beyond null point. Beyond null point, BH greater than B. Therefore B net is equal to BH minus B. Got it? See what a clever question. Many things we are now taking as implications. All these things are used at a time. Of course in your NEET CET, not such two parts of it, only one part is given. B net is equal to BH minus B. Now what about B? You tell me B due to bar magnet. Here we said distance D, B is equal to BH. Now B is equal to BH at a distance D. Therefore for a distance 2D, we use the condition B proportional to 1 by R cube, inverse and cube. Distance doubled. Means inverse means 1 by 2. Cubed means 1 by 8. Therefore B is equal to BH by 8. So the answer is BH minus BH by 8. That is what is 7 BH by 8. Look at this clever example. Many things are used. Many implications we have used. Those examples which we have done as simple examples earlier, those results are used and a beautiful example. Similarly, now let us take the case of bar magnet, again short bar magnet, placed in the horizontal plane but with a difference. Earlier north pole facing geographic north and south pole facing geographic south. Now if the magnet is reversed, what happens? Now even in this case also, bar magnet is placed horizontally, right? Bar magnet is placed horizontally. Where do we get the null point? Of course east and west. One null point we obtain. One null point we obtain on either side. One null point we obtain on either side. Now this is what is the given example. Suppose magnet is placed like this. This is north pole and south pole towards the geographic north. It is given set to be. Now he says P is a null point. P is a null point. Now the question is that if magnet is turned by 90 degrees, what will be the net magnetic induction at the same point P, the point of observation? Now here, before rotation, since this is a null point, our result is B due to magnet is equal to B due to horizontal component of Earth. B is equal to BH at this point P, which is now you will find it as, yes, equatorial point. Remember, now magnet is now rotated. Now when magnet is rotated by 90 degrees, supposing I have rotated it by 90 degrees clockwise or anti-clockwise, now what happens, you tell me? What happens, you tell me? Earlier it was the orientation of 90 degree rotation. What happens? This point P becomes axial point. Equatorial point becomes axial point or vice versa. We have done in the case of rotation of magnet, right? But no change in distance. Yeah, equatorial becoming axial, no change in distance. Therefore, now here B is equal to 2BH. And one more thing. Earlier B is equal to BH and it was opposite because null point condition. Whereas when it is rotated by 90 degrees, what happens? B is equal to 2BH and it will be perpendicular to BH. Yeah, perpendicular to BH. Because now it will be, supposing if it is south and supposing north and south rotation, what you observe at this point P is away from this. Now this becomes B is equal to BH and we always know that BH is from south to north, this is at right angles. Therefore, B is equal to 2BH and perpendicular to BH. Therefore, the net magnetic induction at P will be root of, yes, B squared plus BH squared. So this is what is 2 is there. So it is root 5 times BH. So one more time we have made use of two conditions here. Condition for neutral point, null point, the magnitudes estimate, and then rotation of the magnet is also involved, like that. Now this case exactly opposite to that of our earlier case, like north pole of the magnet facing geographic north. Now this time you see, actually all the discussion should be yours. This is time that you do this work. The south pole of the magnet is facing geographic north or vice versa. North pole of the magnet towards geographic south. Magnetic momentum, short magnet and the same. Now here once again, let me just quick wrapping is axial point, what happens? B due to magnet and is opposite to BH. Earlier we said, remember axial point B and BH were parallel, not facing north. This time it will be opposite. B due to magnet is opposite to BH, therefore net induction is B minus BH. B minus BH, and therefore now it is the possibility of two null points on axial point, one due north of the magnet, other one is due south of the magnet. Therefore you are getting two null points, two null points, one each towards north and the other one towards south of the magnet. Two null points. And what will be the condition? Condition for null point. See, remember this is B due to magnet at an axial point, therefore it is mu naught by 4 pi 2m by r cube. Again, what is that? R refers to distance of each null point from the center of the magnet. Supposing here I said the so-called null point due to equal and opposite. This is BH south to north and this is south pole, therefore magnet. Induction due to magnet, capital B. This R is, remember not the distance between null points. My R is the distance of each of the null point from the center. Therefore in any given example, this is once again, what is that small mistake, the probable mistake to be committed, that he says the distance between null points. Then we use this condition and find the value of R, but answer is not R, it is 2R. So such very important things are to be followed, and I am telling you every time, reading the question thoroughly and fully is very important. Therefore now this is equal to BH, the condition. Once again, momentum of the magnet, distance of each null point from the center, and BH, 3 parameters. Two knowns and one unknown, what you got. Now all these things we talk at axial point. Supposing the distance you got it as R for null point. Now at equatorial point, what will be the case? Equatorial points, you will do it. B at any point is equal to B plus BH. B plus BH. It will be anything inside. Supposing if I take the same distance point, east and west, then what happens? Remember, axial point to equatorial point, intensity, the induction is hammered. Therefore, in such reason, I am writing for at the same distance R, where R is the distance of null point in this case. At same distance point, now east or west when you are writing, B at that point in net induction will be, this is BH by 2 plus BH, because at a distance R on the axial line, neutral point. What does it mean? At that distance R, axial point B is equal to minus BH. Therefore, axial to equatorial have for the same distance BH by 2. So this is what is 3 by 2 BH. Earlier, remember what was the answer? It was 3 BH we got. Now in this case it is 3 by 2 BH is the answer. Similarly, there we have said the case of the rotation of the magnet after attaining. There the answer was root 5 times BH. Therefore, in the same case, null point obtained south pole facing geographic north. Then magnet is turned 90 degrees. Then what will be the resultant induction at the same point, which was earlier a null point, is that B net is equal to root 5 by 2 times BH. Earlier case we got root 5 times BH, right? Rotation of the magnet and net induction Now this becomes root 5 by 2 times BH. Now I have said the case of rotation of 90 degrees. Supposing they have given the case of magnet reversed to pole, that is rotation of 180 degrees. Then what happens? Whether it is north pole facing geographic now or else north pole facing geographic south or vice versa, 180 degree rotation when happens, the net induction at the same point which earlier was a null point will be 2BH, because earlier B and BH were anti-parallel. Rotation of 180 degrees will give the case of BH becomes parallel. Therefore, the answer would be 2BH. Likewise, not only simple location of null points, also linked with other concepts and finding the net magnetic induction is also a very, very popular thing in the case of this. See, last but not least, what a topic one has to say, and the most difficult topic for most of the students. An only discussion of 5 minutes. Follow 5 minutes and then use another 10 minutes for yourself. These are the very simplest examples for NEET and CET. Remember this, only 5 minutes case. Now, the one vector or two vectors which already we have defined in magnetism so far is the magnetic induction vector B bar and the moment of the magnet dipole moment M bar. Remember, both are being vectors and units and all. Remember, now few more vectors and few more parameters with respect to magnetism we will now introduce. And let me tell you, we are not getting into deeper details of all such things. Only on surface level we are doing it for our NEET and CET. Now, remember, what are the few more definitions in the magnetism? Number one is intensity of magnetizing field. Right? Intensity of magnetizing field. Symbol is capital H. How it is represented? H is equal to B upon mu naught. And we are not going into any more details. Why H and how it is different from B and what is the correlation. See, let us not go into details. Only for NEET and CET. H equal to B by mu naught if it is in air, or else if it is in any another medium, then we write it as H by B by mu, such that this mu naught is absolute permeability, that is permeability of air or vacuum, and this is permeability of, yes, that medium we write it as. Now, coming to this unit, I will of course say the unit, SI unit is ampere per meter. Ampere per meter. Supposing you don't remember that, then we have told for B it is Newton per ampere meter, and mu naught you remember it is ampere per meter square, right? If you do the Newton per ampere square, I'm sorry, this is Newton per ampere square, so you will remain with ampere per meter. One more case, remember a very special case, ampere per meter we have. Ampere meter pole strength, ampere per meter, capital H, which is intensity of magnetizing field. Also remember, if this is what is the SI unit we talk about, there is one CGS unit also which we call Eirsted. Eirsted is the CGS unit of capital H, such that 1 ampere per meter is 80 Eirsted. Need not be, but if you want to remember, 1 ampere per meter is 80 Eirsted is also a relation. Eirsted is also a unit for H, but it is CGS unit. Now, what is this H? The name itself suggests this is what is the intensity of magnetizing field. That is, supposing I have a magnetic material, not a magnet, I have a magnetic material. Supposing iron, I say. Now this, I want to make this magnetic material into magnet. Now the agency used to make this magnet, that is what is the process of magnetization, and hence that agency is what is called as intensity of magnetizing field. So whenever we use capital H, what is the consequence? This starts becoming magnet. Now this material, magnetic material becoming magnet, what does it mean? Earlier it was not a magnet because net magnetic moment was 0. Now it is getting magnetized, means what happens? It starts getting dipole moment. Dipole moment such that now to get magnetic moment we need capital H, right? Because of H we get one more parameter that I am writing as I. So what is that I? Intensity of magnetization, which is happening inside the magnetic material. H is the outside agency which is now magnetizing this material. If you take like this in the loose sense, then H gives rise to I. So when does we come across this H? Whenever any magnetic material it is being magnetized, or even opposite to that, to demagnetize also, not only in the case of magnetization, but even demagnetization also we use capital H, such that in the case of magnetization we will get the net magnetic moment in the direction of H bar, whereas in the case of demagnetization we will have H bar opposite to that net magnetic moment. That is why it will be demagnetization. Now H gives rise to this new parameter I, such that I defined as the magnetic moment per unit volume. I have told you even in the last classes also that symbols are very important. In the NCERT book, this capital M used for this intensity of magnetization, which I am using it as I. Don't get confused. See, NCERT book says this symbol is capital M and it has used moment small m, right? So according to textbook, M is equal to small m by capital V, V for volume is also there. I am using I for easy remembrance because it is intensity of magnetization, right? So magnetic moment per unit volume, such that moment ampere meter square, volume and it is a meter cube. Once again, what is the SI unit? So the SI unit of I same as H, that is ampere per meter. Now see, H is a cause, I is a cause and effect. We have many such pairs in physics, right? So this is one such cause and effect. H is the cause, I is the effect. Therefore both have same units, ampere per meter, such that let us remember two things about I. That I always proportional to H. So to have more and more intensity of magnetization, we need to increase the value of H. H increases, I also increases, such that up to a maximum value only intensity can be increased, where all those moments, dipole moments of the individual atoms at atomic level, orientation will be finished, beyond which the intensity or magnetization is not possible. That is what is referred as saturation magnetism. Though we say I proportional to H, I will attain one maximum value which we call saturation for one value of H. So till that we can write I proportional to H, and therefore now we are writing I by H is a new constant. We are writing it as chi. This is not X, this is a Greek symbol chi. Numerator term intensity of magnetization, denominator term intensity of magnetizing field. This chi is what is referred as another important definition in magnetism. This is susceptibility. Susceptibility. I mean, the literal meaning itself suggests something that it shows the ability of that particular material to respond for H. Supposing it is responding very quickly for H, then it is more susceptible. Supposing if its response is lesser for capital H, what is meant by response here? Alignment of those atomic dipoles in the direction of H bar when we are talking about. When that response is very small, susceptibility will be small. So this chi is one more definition, and as you can see the ratio of same quantity chi is the susceptibility, no units and no dimensions. Now you see, to magnetize a material we have used capital H. Therefore now H and I both in a given medium will be parallel. Supposing in the case of magnetization, that H plus I. Why? Because of H plus I. Why H plus I? So because of the parallel nature of I bar with the H. Now I am writing H plus I times this mu is nothing but capital B. This is how we relate the three things. Now this is relate to things, and therefore finally you got B is equal to mu naught times mu r, mu value written as mu naught times mu r, and it is one more time, yes, 1 plus I by h. 1 plus h by, now this is what is capital H. H I have taken common, you see, h by h, and this is I by h times h. And where, no, let me write this as mu naught only, yes. Now we are writing this term 1 plus I by h, which is nothing but chi. So 1 plus chi is equal to a new quantity which is mu r, the one more result. To remove that small misconception, see here I have taken it as mu naught. When we are using magnetizing material, magnetic material to get magnetized, and we are getting this I by h, and that I happens to be inside the material. Therefore now this 1 plus I by h is what is taken to be mu r. This is relative permeability. Relative permeability, which is nothing but mu r is mu, the permeability of the medium over permeability of the air, the absolute permeability, this ratio. One more time you will see ratio of same quantity mu r is again unitless and dimensionless as that of susceptibility. Now this relation is very popular for us. What is the relation you see? 1 plus chi is equal to mu r, the relative permeability and susceptibility, the key words. One is given and asked for the other. It's a very popular case, remember. So all these results, I by h, can be a direct straight question in our NEET examinations. And one more, this B is equal to, yes, mu naught times mu r times h. One more straight example. Or else the relation between susceptibility versus relative permeability is again a very popular case. Now, as a last case, let us do one simple example, because now that we have in magnetism, the three important terms that we have now defined are, one is the case of susceptibility, and the one other case of relative permeability. Now based on these two, now we will have classification of magnetic materials. Let us look into that. See here comes a small comparison table. This comparison table you will see in all your notebooks and our class notebooks and textbooks as well. But here I am making still simpler the comparison table for our examination, what to be remember. Now, what is the basis for the classification of magnetic materials? It is based on these susceptibility values and relative permeability values, such that the category which we call ferromagnetic materials, mu r value very high. Mu r value is very high, very much greater than 1. It is in the order of some thousands. For example, if we consider materials like iron, the mu r values will be greater than 5,000. Of course, it's a number which is unitless and dimensionless, right? So this is very high values of mu r. Then it is what is ferromagnetic. Now we know that relation. What is that? 1 plus chi is equal to mu r, or chi is equal to mu r minus 1. Since mu r is very high, chi is also very high. So high relative permeability and high susceptibility ferromagnetic material, whereas for paramagnetic materials, these mu r values are greater than 1, but just greater than 1. It may be like 1.8, 2.6, something like that. So very small values. So I write here, they are smaller but greater than 1, and therefore chi values are also smaller and it is greater than 1, such that here chi is positive. Because mu r value greater than 1, mu r minus 1 will give you positive values. So susceptibility values are positive for para. Whereas this category, which is diamagnetism, which is absolutely magical thing, is that mu r values less than 1. Mu r values less than 1. Here, what is the physical meaning of mu r being very high or just greater than 1, but it is less than 1? It is the ability to allow the magnetic flux through the material. Mu r value very high means yes, it allows the magnetic lines and it shows greater tendency, whereas mu r less than 1 means yes, it is actually not showing any tendency of allowing the magnetic flux through it, and that is why mu r is less than 1. Since mu r is less than 1, chi values are very small and it is negative. Chi values negative. The characteristic of diamagnetic material is negative susceptibility values. It is positive for both para and dia. In fact, the paramagnetism is a universal phenomena which you have learned with some good details in your chemistry subject as well. Right? Now, what is the origin of this ferromagnetism or this one? Paramagnetism, we said that this is a universal phenomena and it is the existence of unpaired electrons in an atom. Unpaired electron, the lone electrons, unpaired electrons in an atom is the responsible for paramagnetism. When the paramagnetism is more pronounced, that is what is given as ferromagnetic materials, whereas diamagnetic materials, it will be the opposite case. The absence of unpaired electrons is the responsibility for diamagnetism. So this paired and unpaired electrons you do remember. Now, what will be the effect of temperature? Effect of temperature on the values of, it can be susceptibility or it can be capital I, right? All those things now. Effect of temperature, which is very popularly called as Curie's law. The effect of temperature on magnetic materials is called Curie's law, such that in the case of ferromagnetic materials, the relation or the Curie's law will be in the form of chi proportional to 1 by T minus Tc. I am using absolute temperatures. Temperature of the this material, magnetic material or magnet, Tc is a particular constant temperature called as Curie temperature, which is different for different materials. Tc, Curie temperature. Now, what is the meaning of Curie temperature? As temperature increases, susceptibilities will decrease. Here you find an inverse relation that when temperatures increase, susceptibilities are decreasing. Susceptibility decreasing means I values also decreasing, such that at a particular temperature, ferromagnetism, I have told you, it's a pronounced magnetism of paramagnetism. So that pronounced degree will decrease. Therefore, at this Curie temperature, ferromagnetic materials converts into paramagnetic materials, and that is what is called as Curie's temperature. Now, I leave it to you to draw a graph for this. How do you get the graph is a very important thing. Please do it as homework and if you want to ask me. Whereas for paramagnetic material, the Curie's law, yes, obeyed, but it is in the form of 1 by capital T. Chi proportional to 1 by T will be the case for the paramagnetic material. Look at this difference in the denominator. Of course, I am writing you all these temperatures in absolute this one. And now for diamagnetic materials, yes, it is no question of Curie law. No Curie law in the case of diamagnetic materials. Therefore, it is now a homework for you. Temperature versus chi. It is not X, I am sorry. This is chi, the susceptibility versus temperature. For different cases, you please do it because already it is there in your notebook, OneNote, and you can go through that. Now, examples also for ferromagnetic materials, paramagnetic materials and diamagnetic materials, please go through your NCERT book because those names are very, very popular. What all those names given under a particular category, you please underline and read it. It can be a very direct conceptual question for you. Supposing if it is asked copper is diamagnetic or paramagnetic, ferromagnetic like that, or water is like that, or which of the following is diamagnet or paramagnet like that. And you know that most of the D black metals are paramagnetic, and ferromagnetic you give only 3 examples like aluminium, cobalt, nickel, or the alloys made of them. When it comes to the question of other D black elements, most of them are of course paramagnetic, but there are some diamagnetic materials as well. Please go through all of them and you make a note of that.